Today we want to wrap up our discussion on clustering. It should not take more than 5 minutes. And then we're going to start talking about some more fancier latent variable models. So first I'm going to show you how I think clustering is also a latent variable model. And then we're going to talk about more of those. Okay, so if there are no questions, let's get started. So last time we looked at clustering, right? We looked at the problem of clustering, and then we looked at one algorithm for clustering. There are many more, right? So k-means is not the only one. There are many more, but k-means is sort of the one that's kind of easiest to understand. It's very sort of natural, right? So let me put this algorithm up here again, and so this is how it works. So what you're trying to do is you're trying to cluster data, right? So you're given some n data points. They all belong in some d-dimensional space. So they're all described using d attributes or features. And you want to place them or partition them into k clusters. So one way to do that is k-means. And the way k-means works is you start with, so there is a notion of a centroid in k-means. So centroid is a point which kind of represents a cluster, right? And it could be a point that is in the training data set, or it might not be. But anyway, it represents the cluster. So you start with k initial points, and then at every step, there are two steps to it, at every iteration. First step, you assign every point to its closest cluster. So if you look at point number 2, right, this assignment step, you're essentially taking every data point and you're trying to see what is its distance to every centroid that you have, right? And then you are finding the minimum k and saying this is the assignment. So this point belongs to this cluster. So you already see that there is a need for a distance metric here, right? And typically if your x is in d-dimensional space, then this distance metric is could be Euclidean distance. But there's no, I mean, you can replace it with something else as well. And then comes the third step where you revise your cluster center. So now you have a set of points that belong to a cluster, and now you revise your cluster center and using all the points that are assigned to cluster K. So now this is a little general, like how do you revise it? So one way to do it, which is a very standard way in k-means, is you just compute the centroid of your point. So centroid essentially means that you have d points, and you have some number of points in your cluster, and each one is a vector of d dimensions. You just take the column mean, right, and that becomes the centroid. But there could be other ways to do that as well, right? And then you keep doing that until your cluster doesn't change too much. And I'll show you how to quantitatively figure out when you have converged. But this is sort of the general sketch. Now you can apply it to any other data as long as you can come up with some distance metric, right? And you can come up with some way of computing this representative, right? So in some algorithms, what happens is that, let's say if x is not a vector, right? Let's say x is is a text, right? So then you could come up with a distance metric, right? So if you have taken information retrieval, you might have seen how you compute like a feature representation for text, right? You could do this what do you call it, vectorization of documents. So you could do that, and then you can revise it, right? And sometimes what happens is that you might have a distance metric, which is fine, but where people get stuck is how do you compute the representative, okay? So and oftentimes instead of taking this centroid, people take what is called midoid. So midoid is a point such in a group of points, a midoid is a point which is closest to all of them. So if you compute, so you take every point, you compute its distance to every other point in that cluster, and whichever gives you the lowest total value would be the midoid, right? So that could be another way to find the representative. But of course, that will take longer time because you have to compare everything to everything else. K-means in its vanilla form is very efficient because you are, in every step, all you're doing is you're computing distance to k centroids, right? So it's not too many distance computations. And then you're just doing a revision, which is essentially a column mean. So it's pretty easy to, it's very efficient in that way. All right, so as I said, you can have other variants of k-means. Now comes the question, what are the parameters of k-means, right? So as I said, one of the most important parameter is k, which is the number of clusters that you want. And then of course also the similarity or distance metric, but that is something that is like a hyperparameter. You kind of, it is determined by what kind of data you have, right? There's not too much of flexibility there once your data is defined. But k is something that you will have to provide, and there is no easy way to find that. So a standard way to do that is through trial and error. So you try different k's, and whichever gives you the best performance, you choose that k. So the question becomes, how do you evaluate the performance of a clustering algorithm? And there is a standard objective function to do that, right? So objective function looks like this. For every point, what you're doing is you're essentially computing its distance to its centroid, right? And you're just adding them up, and whichever gives you the lowest value is the best cluster. So for example, right, so for example, let's say this was your data. Let's say your data had just 2 clusters, and it had 10 points, right? And let's say one clustering algorithm gave you this output. It said that point this, and this belong to one cluster, and this and this. So 1, 1, 1, 1, 1, and these belong to another cluster. All right, and let's say it told you that the centroids are. Now remember, since you're taking a centroid, so there is no guarantee that the centroid will be one of these points, right? Because you just take a centroid. So let's say it says that this centroid is over here, so this is C1, and this centroid is over here, this is C2. So how you evaluate this clustering methodology is you essentially take the distance of every point to its centroid. So this distance, square of this, plus square of this, plus square of this, and this. So that gives you one part, and then all of these distances, and then you add it up. So clearly what you'll see is that this value will be large. On the other hand, am I making this noise? Excuse me. Pretty annoying. So it was the sound of my brain coming out. It's better. All right. So on the other hand, if you had the same data set, however, and let's just put it here, and let's say another algorithm said that I'm going to call all of these as 1 and all of these as 2, and these are my centroids, then if you compute the objective function, that will be lower, right? So that is the idea. So that way, what you can do is, you given any data set, you try different k's, right? You run your clustering, you compute this objective function, and then draw this plot where this could be your objective function value, and this could be your k, right? And it would typically go like this, and then wherever you see like a knee, right? We call this a knee. Wherever you see that after this point, number of clusters is not really helping us, you'll say, okay, that is an optimal number of clusters. Right? The reason the clustering quality will decrease like this is because use this. Hello. Okay, let's try this. So the reason this quality will decrease like this is because you can see that as you increase the number of clusters, you would be able to do a the job. So on one extreme, what you could do is you can try to find n clusters, right? Where n is the number of data points you have. So clearly, each point will be a cluster by itself, and that will have zero error. The objective function will be zero because everything will be right on top of their centroid, right? So that's one extreme. Another extreme is where you say there's only one cluster, right? In which case you will just get one centroid and that value will be the highest. So you want something that's in the middle. And the only way to do that is by doing this, exploring this whole space. And typically you don't explore the entire space. You go from 5 to, something reasonable. All right, any questions so far? Okay. All right, then of course, we talked about this last time, is that there could be initialization issues. Depending on where you initialize your cluster centroids, sometimes you might not get the right answer. So even in the example that I showed last time on my notebook, right, oftentimes what happens is depending on where you start with, sometimes the answer that you get might be very different. So I tried to do that last time, right, but you might have to run it many times. Okay. All right. So for this demonstration, this was my data that I started with, and let's say these are my initial centroids, right? Let's say I take 4 centroids because I know there are 4 natural clusters. Can you hear me without this? Yeah, okay. So when I run clustering, this is how it works, right? So yeah, good. So I started with some number of four centroids. 3 of them were here, 1 of them was here. And what you will see is that after I run it for many iterations, this is the answer that it gave, right? So it didn't give us the answer that we wanted. And that was because we didn't start with a good initialization, right? Next time I might run it with a different initialization, let's say this one, right? And let's try if it gives you the right answer now. It didn't, right? And then, so that is the point. So clustering is very sensitive, or k-means is very sensitive to how you start, right? And then there are some smarter ways to start. So if you look up a little more literature on clustering, you will see you could either make multiple runs, right? And then find out the one that's best, or you can choose the centroid in a very smart way. For example, this strategy where you start with one centroid. So choose one point here, choose, let's say this is the one point you chose, then the next point would be the one that is farthest from this in this data set. Then the third point would be something else, fourth point would be something else, and so on. So that might, there's no guarantee still, but it might, there's less likelihood that you would fail. Any questions? Okay, so of course k-means is a very nice algorithm, easy to understand, easy to implement, and it's very efficient. It's also easy to parallelize. So if your data is very big, you can come up with parallel solutions to do k-means. It works very well in that setting. And you can extend it to other type of data. As I said, you can replace the distance, Euclidean distance, with something else, and how to compute the representative with something else, and you can come up with a brand new k-means algorithm, right? In fact, one of my PhD students recently developed a new k-means for time series data, where instead of comparing time series, it's hard to compare 2 time series. Time series are essentially sequence of observations with time on them, right? And he came up with a very interesting way to do that with k-means. Okay, but there are some weaknesses. One of the weaknesses that you get with k-means is that you always get circular clusters. And the reason you get circular clusters is because it measures this distance, right? So this distance is like putting a circle around the centroid, right? So that is the idea. So if your data has a slightly different form of natural clusters, so for instance, if your data looks like this, so one set of points is like this, right? And the other set of points, let's say, is like this. Now to us, to humans, it's clear, even if I had not used two different colors, it's clear that there are two different clusters. But if I run k-means on this, k-means would most probably like get a cluster here and get a cluster there. So that's how it works, right? So that is an issue with k-means. Then there are some other variants of k-means which use like a kernel function inside, and they are able to learn non-circular clusters as well. But in its plain vanilla form, there is this issue with k-means. Sorry. Okay. Another thing, as I said, was that choosing k is not principled. There is no principled way to do that. There is no guarantee that you'll get an optimal result. See, clustering by itself is an NP hard problem, right? Because you're trying to find the assignments such that this value is minimized, this value, right? But k-means does not directly optimize for that. It's a heuristic, so it might not always give you the right result. And another issue with this is that k-means is what we call hard clustering, which is that it assigns every point, it forces every point to belong to one cluster, right? So that is what we call hard clustering. The other side of hard clustering is what we call soft clustering, where we say that every point could belong to multiple clusters. Sometimes that works. That is more natural, right? You do not want to force every point to belong to exactly one cluster, but you want it to be a little relaxed, saying, okay, this point could be in this cluster or this cluster or this cluster. So a generalization of this is that what we want is that every point can belong to every cluster with some probability, right? So then, so what k-means essentially does is that, let's say you have k clusters. Let's say these are clusters, like 1, 2, 3, let's say 4. Let's say k is 4. So for every point, what k-means says is that it belongs to cluster 3, for example, with probabilities 1 and with probability 0 in other clusters, right? So that's why we call it hard clustering. But sometimes it might be nicer or more natural to come up with solutions which say that it belongs to cluster 3 with probability high and then others with probability low. Maybe sometimes this might be high as well, right? So that gives a little more nuanced view of your data rather than forcing everything to be in one cluster. But k-means does not do that, and what we will see now are algorithms that you could use to do that. All right? So that is what we call probabilistic clustering or model-based clustering, where what you're trying to do is figuring out this probability. What is the probability of every point to belong to every cluster? And of course, that becomes sort of a harder problem. Yeah, go ahead. Right. So the question is, how do you move your center around? So the answer to that is there is no probabilistic form of k-means. So we don't actually apply k-means in this setting. So we'll have to come up with new clustering algorithms to do that, because you're right, that becomes an issue, how to move things around. All right. And you can think of k-means or hard clustering as a special form of this, where you are forcing only one probability to be 1 and everything else naturally becomes 0. All right, so this is sort of the end of k-means. So let me just take a moment to see if there are any questions about clustering. Yeah. Yeah. Right. So the question is, this is an objective function, right? And it is a function of the unknowns that we are interested in, which are your ck's, right? So can we use like a mathematical optimization method to find the optimal value, right? But the problem is that since the ck's, first of all, you'll have k unknowns, right? And it's very hard because r and k also contains ck, because r and k tells you which cluster xn belongs to, right? So this whole thing as a function of ck is fairly complex to apply any standard mathematical formulation, because just See, here this R and K is here, right? So R and K is 1 if Xn belongs to Ck, and R and K is 0 if Xn does not belong to Ck, right? And belongs to and not belongs to is determined by this value, right? Whichever is the minimum. So it becomes a very nasty objective function to really apply. So that's why we rather go with a more heuristic fashion. Exactly. So the objective function will become very, because it won't be smooth, first of all, right? Because there is this, whenever you see things like this in an objective function, that means it can take value 0, it becomes like a step function in many places. So it will be very hard to optimize over this. If you could do this, then you're basically trying to solve an NP-hard problem, and you'd become a superstar. Question? Right. You could, right? So the question is, what if instead of, so basically what happens in soft clustering is that instead of this being 1 and 0, right, you are going to make it like P and 1 minus P, right? So yeah, so then it becomes a little easier problem, and that's what we are going to solve next. So k-means by itself can't be used here, but we will come up with a different variation which is kind of like k-means, and I'll show you why they are similar. Good questions. All right, any other question about clustering? All right, so there goes clustering. And now we start with the real fun, which is latent variable models, right? So let's start with an introduction. So latent variable models essentially assume there's a word latent there, which means there is some hidden parameter, right? So let's first start with a sort of a step back. So we have done this before. Let's say we have some distribution, right, which is parameterized by some parameter. So let's, for example, if this distribution was a Gaussian distribution, then theta would contain mu and sigma, right, which are the two parameters. And now you can generate samples from this distribution, right? You can take the distribution and generate samples, and then you can see how they look like. For example, in this other workbook, maybe I don't have that, but you could do that, right? You know how to do that part, right? But let's say we have a slightly different generative process where you have a hidden variable z, okay? So what happens when, now if you want to find your x, what happens is first your distribution generates this hidden variable, all right? So this hidden variable is also random. So your distribution first, you crank your distribution thing, it gives you a z, and then based on z, you choose another distribution which gives you x. So x is what you observe. So you can think of linear regression like that, right? So if you remember the Bayesian linear regression, what you do is you have some distribution posterior for your w's, right, the weight vectors. So how do you get a y? First you crank this posterior for w and you get a w. This is a weight vector. Then you combine it with your x and you get a y, right? Or actually, then you combine with an x, and that becomes the mean of a new distribution, and then you sample from that, and then you get a y, right? So that's the generative process for your regression. So in the same way here, you are saying that you have some hidden variable that actually controls your y, all right? So let's go back to our example that we looked at on Monday, which was about the magazine example, right? So imagine that you're an editor for a magazine, right? So now what you're going to do, so class what we did was that, okay, if this editor wants to compute, or editor wants to create a new issue of the magazine, let's say this is Time magazine, what she would do is she would call all of her sub-editors, sub-area editors, each one would give her a few articles from their thing, and then she would put them together. But now let's say she's doing it in a slightly different way. Let's say she has an access to this probability distribution, which gives her an article. So direct model would be, if she wants to create an issue, let's say she wants 10 articles in her issue, she'll just crank that distribution 10 times, get 10 articles, and here's your Time magazine. But other thing could be that, let's say, instead of doing that, she has this two-step model where she has one probability distribution that tells her which topic to choose from, right? So we'll call that latent variable z. So the first thing she does is that she has one distribution that gives her z. So let's say there are k topics: politics, history, sports, and technology. Let's say there are 4. So she has a distribution which is probably a multi-nully distribution, which will give her a number between 1 and 4. Then now what she has is, on this side, she has 4 distributions for each one of these topics. So this z will tell her which box to choose now. So she'll take one of those boxes, and then she'll say that, okay, I'm going to sample a topic from, or an article from this particular topic, right? So just to make it a little more clear, so she has so she has a distribution or a probability distribution for z, okay? And then here she has 4 distributions. One is, when probability distribution to give you x, which is your article, given z is 1. And probability to get x given z is 4. She wants x, right? So what she will do is she'll first sample a z from here. Now z could either be 1, 2, 3, or 4. Then she will sample from the corresponding box an x, right? So that's how this two-step process works. So earlier all she was doing was she had one distribution, which was p of x, and she was just sampling from there. Now what she'll do is, let's say she has to generate 10 articles. She will first sample one z from here, and let's say it comes out as sports. So she'll go to the sports box. Let's say this one is sports. Then she'll sample an article out of there. Then she'll again sample z again. So let's say z is again sports. So again she will sample one article from the sports, then technology, and so on. So what you will see in the end is that the distribution of topics will follow this distribution, right? So let's say this distribution here was like this. It was high on sports and very low on politics, technology, and I can't even think of health, right? So let's say this is like one of the ESPN magazines. So high on sports. So what will happen is that eventually when she samples 10 topics, most of them will be sports according to this distribution, and then within that she will have a distribution, right? So let's say this is our model. So basically what I'm doing here is I'm introducing a new way to generate data. In the past, what we have done is we have said that we have one px and we sample from there. And then the problem that we have dealt with is that given some data, how do you infer the parameters of this distribution, right? That's what we did for the coin toss or the Gaussian distribution and so on. Here what we are going to do is the same thing. Given some data x's, right, how do we figure out the parameters of not only these but also this, right? So it becomes a little more challenging problem because you don't know. When you see the articles, right, when you see the Time magazine, you don't know which article belongs to which category because it's a hidden variable, right? What you want to do is, looking at that, figure out what were the parameters of these individual distributions as well as what is the parameter of this z, all right? And the reason, okay, so that's sort of the idea. And the way it will help us for clustering, for instance, is that if you could do that, then you can figure out, okay, for every data point, which z did it come from, right? And since this is all probabilistic, what you will do is you will be able to find what is the probability of z equal to 1 given x. Okay, so given an article, what is the probability that it came from sports? Then you can compute probability of z2 given x, z3 given x, and z4 given x. So this gives you a natural way to do the soft clustering because it's essentially giving you a distribution over your hidden variables. All right? So that is the idea. So let's see how to do that in a more mathematical way. Okay. So this is the point where we want to start latent variable models, and this is a pretty large topic, right? And we are going to explore some parts of it. Clearly, we can't explore everything. But what I want to do is first set up the stage where you can see that it's a pretty large area, and then we'll take some specific examples. Right? So the idea is that you are observing something, and we call it X. Okay? So X is something that you observe, and the value of X depends on some hidden random variable Z, something that you do not observe. And we assume that Z is coming from some distribution over Z, P of Z, and X is then coming from Px given Z, right? So what happens is that if you assume different forms for these Z and X and these probabilities, you will get different latent variable models. So for instance, if I assume that Z can take 1 out of k values, let's say I assume that the example that I showed earlier. So Z takes 1 out of 4 values. If we assume that, then this latent variable model is called a mixture model. Okay? If we assume that Z can take any value, a numerical value, then that model becomes what we call factor analysis model. And then there is a certain special form of factor analysis model which gives you principal component analysis. And if you assume that Z comes from a Dirichlet distribution, so that is something that we will not see, but that becomes what we call a latent Dirichlet allocation model. That is very popular in topic modeling. I don't think we have talked about it, but don't worry about it. But the main point is that by making different assumptions about Z and X, well, not exactly assumptions, but by using different forms of Z and X. So X could be a vector, X could be a value. Similarly, Z could be a vector, Z could be a value, Z could be categorical or numeric. Depending on different combinations, you will get different models. All right? So today we are going to look at the first one, which is mixture model, and then we are going to look at factor analysis and PCA later on. All right. So let's start with the mixture model. So in mixture model, what we assume is that your Z takes 1 out of k values. So you can think of Z as a latent state because it takes discrete values, right? And then there is a distribution for Z, and clearly since Z takes 1 out of k values, one way to represent it is using a multi-nully distribution, which is parameterized by a vector pi, right? If you remember back, a multi-nully distribution lets you model a roll of a dice, right? So let's say you have a k-sided dice. What is the probability? So the face, the value on the face of this k-sided dice is your random variable, right? So it can take 1 out of k values. And the probability for each one of them is inside this pi vector. So this vector will have k elements in it, and each one will tell you what is the probability of getting that corresponding face, right? And then the Px given Z is given as, we just write it like this. So let's say this is, what is the probability for X to take a value X, or a density, probability density of X when Z is K. So this is like one of those boxes that I talked earlier, right? Later on, I'm also going to write them as this just to save some notation. So when you see a subscript K, basically it is the probability distribution for X given state K, all right? So now if I want to compute the probability for X, right, without knowing Z, you can compute it by marginalizing it over all possibilities of Z, right? So basically it's like an expectation over all Z. So this will be like a weighted sum. What is the probability of observing state K times what is the probability of X given K? And that's sort of the total probability, all right? So you can think of pi k. Pi k is the kth element of pi, right? So you can think of it as a mixing weight. So you can think of it like an expert model where you have k experts, and you're given a new X, and you'll say, okay, the probability of this X will be how much does this expert think it should be coming from this times what is the probability of this expert, which is the mixing weight, or pi k, and then you sum it up, right? So it's like a weighted average. Okay, so now what we want to, okay, and then how do we use it, right? So what uses this mixture model? So there are two broad uses. One is, of course, you can use it to just estimate Px given theta, which is here, right? So this is the probability, right? You can use it in your naive Bayes model, right? For example, instead of in the original naive Bayes model, we always assumed that X is coming from one distribution, right? Or even in our latent, the LDA, QDA kind of setup, right? The discriminant analysis, we always wanted to find what is the probability of X given one class, right? So you can compute this probability by assuming that within the class there are multiple components to it, and you can do that. So that is one use. And another use, as I said earlier, is to use it for soft clustering, because what you can do with this model is, after you compute Px given theta, right, you can apply Bayes rule to it. So we know what this is, and we know what Pz is, which means that we can apply Bayes rule and compute what is Pz given equal to k given x, right? We know how to do that. And with that, we will be able to do our probabilistic clustering or our soft clustering. All right. The question becomes, okay, how do we compute each one of these things? And here, as long as you have a nice way of writing this out. For example, in our previous example, we said this is going to be a multinomial. So this is easy, right? This is just going to be pi k. This value is going to be whatever we assume each class conditional or each state density model is. So this one. So in fact, today what we are going to assume is that x is a vector, which means that we can replace it with a multivariate Gaussian. So, but in other data sets, you could use a different type of model as well. All right. Any questions so far? All right. So this is how it looks like in sort of in the generative form, right? So what you're assuming is, so now we're going to make it a little more specific. So what we are assuming is that your hidden variables are coming from a multinomial distribution, which means it takes, and let's say there are only two possible states, okay? And your x given z are Gaussians, okay? So what we're going to do is, we are going to simplify things. We are going to assume that x is just a scalar observation, a number, and x given z equal to k, or this value, is just a Gaussian, okay, a univariate Gaussian. So which means that if you have k equal to 2, if k takes two values, you will need one parameter to represent pz, right? Because pz will be a random variable, or z will be a random variable which takes two values, 1 or 2. So you can represent it using actually a Bernoulli variable with 1 pi. So here pi is 0.5. And then for each state, I need a mu and sigma. So let's say I have one mu here, sigma here, and then mu2 and sigma 2. So now I can use this to generate samples. How would I do that? First, so let's say I want 1,000 samples, all right? So what I will do is, first I will sample from this Bernoulli distribution. So this Bernoulli distribution will give me either 1 or 2. I'll toss a coin, right? Then depending on what I get, let's say I get a 1, I will sample from mu1 sigma 1, the first component. If I get a 2, I will sample from the second component, and then I keep adding it, right? So if I keep doing that for 1,000 times, and then I just plot a histogram to see how my data is distributed, this is how it will look like, right? So what you'll see is that you get a bunch of points from this. So this is one Gaussian, and this is another Gaussian, right? So if I change my pi, instead of 0.5, I make it 0.1, and then I do this sampling and this, you will see that the empirical distribution has changed, because the number of times this component was selected would only be 0.1 of the total, right? Or expected number of times. So it would change, and the same thing, you could try that. And then also, if I change these individual parameters, so instead of sigma 1 and sigma 2, let's say I make my mu2 or sigma 1 to be 0.5, so a little larger variance. So you'll see that my first component becomes a little fatter, right? And the second one is still slender. So that is how the generative process works. But this is not what we are interested in. What we are interested in is the reverse problem, right? What we are interested in is saying that if I give you this data, right, the data that generated this histogram, how can I figure out what is pi, what is mu1, what is sigma 1, mu2, and sigma 2, right? So that is the learning part. And we are going to see one algorithm to do that. We call it expectation maximization, or EM, which is a very elegant solution, and it is applicable not only here but in many other settings, right? Anywhere where you have some hidden values, hidden variables, any latent variables, expectation maximization is a very useful way to estimate the parameters. All right, so we'll look at it from the perspective of mixture models only, and then I hope that you will be able to generalize it to other settings. All right, so this is sort of, all right, so this was the forward process. Now we are going to look at how to do the reverse process. Any questions so far? Okay. So this is the task. So obviously, if your data had only one mode or only one component, then you know how to do this, right? If you assume your data is Gaussian, I can take my data and I fit a Gaussian, which is you compute the MLE estimates. Very easy. But what if it has multiple components? Which means that I can still fit a Gaussian, but I won't do a very good job, right? For example, here, let's say I have these two data sets. So this is just very simple data sets, right? If I fit a Gaussian, this is one data set, this is another data set. This data set obviously only has one component, right? If I fit a Gaussian, it does a very good job, right? It learns that this is the mean. So this red line is basically the PDF that I have plotted from the Gaussian that I have estimated. So if you look at the code here, right, all I'm doing is I'm fitting it. So I'm getting a mu and sigma from this data set. Does a very good job because the data was coming from a Gaussian. But when it is coming from these two components, then this data is not really coming from a Gaussian. Now you can fit a Gaussian, nothing is stopping you, but this is what you will get. And you will see that it's not doing a very good job, right? Because it's giving a high probability in this area where you observe no data at all, right? So that is the point. So now how can we solve? How can we estimate this without making that mistake? So what we need is this, right? So let's say my data, if I knew what was my Z, right? If I had told you which point is coming from which component, then the problem becomes very easy, right? Because if I know that these points are coming from component number 1 and these are coming from component number 2, you can just separate them out, right? And learn individual MLEs and plot them, and you will get two nice red curves here. So what you would do is, if I give you that, okay, all these points came from component number 1 and these from 2, then you would just do two separate MLEs and draw two red bells here, right? Fantastic, no problem at all. But that is the problem, that we don't know the ZIs, right? So how do we figure out those things without knowing ZIs? Yeah? If you want to do it in a brute force way, you can do that, right? You can explore all possible combinations of ZI. So let's say you have 100 data points, so you have 100 ZIs, right? So you can try out every possible combination of ZIs and estimate two Gaussians every time, and then see which one fits the best. But that's of course not a very computationally feasible approach. The other thing is that you can always compute the log likelihood of your data, right? And try to optimize it, right? But what we will see is that it is actually very hard to compute the log likelihood. So let's see what the log likelihood looks like, right? So remember, what we want to do in maximum likelihood estimation is that we want to maximize theta that maximizes our log likelihood. Right? Now, what will be the log likelihood of my data set, right? So let's actually do it here. So log likelihood of my, so let's first say, what is the probability of any data point, xi, given this model? Right? I wrote it out earlier. So this is going to be the weighted probability, if you remember. The probability that it came from the mixture component number k, and then the probability of that mixture component, right? And then the mixture and summation of this from k equal to 1 to k. Right, so this is the probability that you get. Which means that if I now want to compute the likelihood of my data, likelihood is just, I'm going to call it L, is just a product over all my data points, right? 1 through n, and then summation pzk pk xi given theta, right? And then I can take a log here and just compute, this is a function of theta, the log likelihood of your data. And the reason we take log is then this product becomes a summation. So it will become summation I equal to 1 through n log of summation p zk pk xi theta. So after you go back to there, I want you to look at this again and just make sure that you are convinced by this, right? So this is sort of the equation. So this is an equation which is equation of theta, which is a function of theta, right? Which means that in principle we should be able to apply some optimization method, because this is smooth in theta, right? This will be so theta contains all of our parameters. It will contain the pi and mu1, mu2 and so on. But the problem is that because there is a summation inside the log, doing a derivation of this becomes very hard, right? We are not good as mathematicians taking derivatives of functions in which there is a summation inside a log. That kills us, right? Because if you think about it, if you have log and then you have x1 plus x2 and so on, if I take a derivative with respect to, let's say, x1, I will first take the derivative of this. It will be 1 over x1 plus x2 plus x3. That is more complicated than that, right? And then the derivative of this part. So it kind of becomes a very messy proposition, which means that you cannot really apply things like gradient descent on this. It doesn't work very well. And that's why we need methods like EM. So next time I'll talk about EM, but today I just want to show you that even if you were able to apply a mathematical optimization on this, right, it won't work very well. So in optimization methods, we have so far seen gradient-based optimization methods, right, where you compute a gradient and then you feed it to your minimizer and it gives you the answer. So we have used conjugate gradient descent for that. But there are other methods as well. So for example, there are methods in which you do not really the gradient. So those are called non-gradient based methods, where you sort of, or you numerically approximate the gradient. So there are lots of methods like this in that library. So what if I use that, right? So I just want to show that to you. So let's say our data was this, and let's try to minimize, or actually we want to maximize this log likelihood, right? Oh, you're not looking at that. It's all fun. All right, so let's say this is our data, right? So I could compute the log likelihood of my data set using the previous equation. So if you go to this formula, all I'm doing is I'm just sort of taking the log and adding it up. And this PDF model is here. So this is doing exactly what I wrote earlier, right? So it's taking zk, which here there are only two classes, so it will be 1 pi and 1 minus pi, times the PDF under that. So that's the pk of x given theta and the other one, right? So this is how you can compute the log likelihood, and you can feed it to a minimization function which does not require the gradient, right? So in your examples, when you do your programming assignment, right, you were writing these kind of obj functions, but it used to return both the value and the derivative, right, the gradient. But there are other ways where you do not have to specify the gradient at all, right? You must be wondering why I didn't tell you that before. But anyway, so those ones are sort of approximate versions. So if you apply that here, what you will see is that it does not converge. Why? Because this objective function is very weird. It has it's a summation of the log, which means that it becomes it's not convex anymore. Right? So it's very hard to find the optimal. So this one doesn't work. So that's called BFGS, after somebody's name. Powell does not work. There's Nelder-Mead, which kind of works actually. If you look at it, it does things in a slightly different way. But this is also a slightly simpler problem because you have only two components and very few data points. So it's able to do something and actually reaches pretty close. So this is the answer that you get. I didn't tell you what the order is, but this is the pi, right? And this is mu1, this is sigma 1, mu2, sigma 2. So if the data that I generated actually came from, where is it? Here.
the pi was actually close to 0.3, and mu1 was 0, mu2 was 0.6, sigma 1 and sigma 2. So it gets close. But there's no so it doesn't work very well when your data is larger and you have more components. But for this one, kind of gets closer. If you apply this other function, it doesn't converge, right? So the point here is that if you directly try to optimize this objective function over here, it's very hard. So what we will see next time is an algorithm which tries to solve it in a more like 1-2 dance fashion. So it first assumes that we know our zi's, right? No, it first assumes that I know theta, I know the parameters, and it finds out what would be the best zi's. Then it recomputes theta, and then keeps doing that. It's very much like k-means, right? But it does it in a more probabilistic fashion, and you can show that it will always try to go towards the optimal value. All right? So we'll look at it next time. Are there any questions? Fantastic. So I'll see you on Friday. Thank you very much.